All right, and I am back. And here we're going to continue with our review, or I should say, with the studying of chapter 2.4. And what I'm going to do is I'm going to cover the content of the chapter first. In other words, I'm going to go over and read the chapter, and then we're going to try to answer some questions. The questions as usual. The book is in the video description, so go ahead and download that now if you'd like. You could also order a copy. It is a great book. So, like I said, check out the links in the description. And I don't get anything for it. I'm just saying support the author. If you want to get a physical copy, like I have one, it's very nice. And if you want to just look at the answers right now, as before I even know if the answer is or not, just go to the back of the book. Just download the book and let's do it. 2.4. All right, we are doing, this would be interesting, biconditional statements. All right, I'm going to read it now. It is important to understand that P implies Q is not the same as Q implies P. To see why, suppose that A is some integer and consider the statements A is a multiple of 6 implies A is divisible by 2. A is divisible by 2 implies A is a multiple of 6. Okay, so when you think about the first one is P implies Q. Okay, I'm not a mathematician. I'm a landscaper and a university student pursuing a double bachelor in pure math and computer science. This is a class I didn't pass, so I'm just saying all this to keep in mind that I'm doing this as a study session for myself, and anyone else that learns is great. But anything I say, take it with a grain of salt. Don't go quoting me to a professor. Anyway, so here we go. What I'm trying to say here is that I think of P and Q as cause and effect. P is the condition and Q is the result. So, for instance, A is a multiple of 6, okay, implies A is a divisible by 2. So what are the multiples of 6? Well, we have 6, 2, and 3, and 1. So those are the multiples of 6, and implies that, well, okay, when we think about a multiple of 6, 1 isn't really, when we think of multiples, I guess 1 doesn't really count. I mean, it's, at least in the way we think about, in other words, like this. Let's say here 6, you can say 2, 3, and 6. Now, I mean, we could say 1. That's fine. For our purposes, it won't matter. So we're going to say if A is a multiple of 6, and what I'm doing here is I'm working through what they're saying here to try to understand it myself. So keep that in mind. A is divisible. And the reason why is not, here we go. P implies Q. So it's like this. If A is a multiple of 6, and we know that 6 is even, so I'm not going to write this down because it's not relevant to this discussion, but how we know that it implies that it's divisible by 2. What is the implication from? Well, we know that 6 is an even number. A is a multiple of 6, meaning A itself might be, I don't know, 18, for example. But we know that 6 is even, and evens are all divisible by 2. By definition, and a number is even if it's divisible by 2. So basically, yeah. Right. Now if we continue, A is divisible by 2. That was a terrible 2. Implies A is a multiple of 6. Okay, so this is Q implies P. Now, if you look at it, A is divisible by 2, so it could be 2. It says that implies that it is a multiple of 6. I don't know. It's not necessarily true. 4 is divisible by 2. It doesn't mean it's a multiple of 6. It's not. Now, continuing reading here. The first statement asserts that if a is a multiple of 6, then a is divisible by 2. This is clearly true for any multiple of 6 is even and therefore divisible by 2. By the way, I didn't read all this stuff. I was just working off the knowledge I already had. But it's funny, they're going with the same thing. It's page 46, by the way. The second statement asserts that a is divisible by 2, then it is a multiple of 6. This is not necessarily true for a... Are you kidding me? Wow, this is so hilarious because a equals 4, for instance. Yeah, they literally said everything I said, which I swear I didn't read it. At least, maybe I subconsciously remembered this from class that I took, maybe like, what was it? 6 months ago? It's possible. I try to pay attention in class. But anyway, reading that sentence. This is not necessarily true for a is equal to 4, for instance, is divisible by 2, yet not a multiple of 6, yes. Therefore, meanings of P implies Q and Q implies P are in general quite different. I'm going to read that one more time. This is important. Therefore, P implies Q and Q implies P are in general quite different. So, yeah, that's important. The conditional statement Q implies P is called the converse of P implies Q. So, a conditional statement and its converse express entirely different things. But sometimes, if P and Q are just the right statements, it can happen that P implies Q and Q implies P are both necessarily true. For example, consider the statements A is even, and that implies A is divisible by 2. Okay, and then we're going to say A divisible by 2, which implies A is even. So Q implies P. No matter what value A has, both of these statements are true. Since both P implies Q and Q implies P are true, it follows that P implies Q and Q implies P is true. Let's introduce a new symbol, the biconditional, to express the meaning of the statement P implies Q and Q implies P. So we can say this. So I'm going to write the biconditional down here. A is even. A is divisible by 2. All right. Right. According to the previous section, Q implies P is read as if P if Q, and P implies Q can be read as P only if Q. So, let's see. P implies Q can be read as here we go. P if Q, P if Q, and Q implies P can be read as P only if Q. Okay, and the biconditional could be read, IFF, okay. I'm just going to say P if Q. So IFF means if and only if. So just I'm going to write it up here. IFF means there we go. So we have P implies P if Q, P only, wait a minute here. Let me make sure we wrote this all right. P if Q, yes. P only if Q. And finally, P if and only if Q. So basically, we have here is the integer a is even if and only if a is divisible by 2. Which, yeah, that's actually a very important point. We use that a lot. This idea that if and only if it is divisible by 2, does that make it an integer? And this is something that we'll come back to later in our future classes. All right, let's I'm going to try to squeeze in the truth table here. Okay. P only if and only if Q. Q. All right, so we have if P is true, Q is true, true. Do true, true, false, false, true, false, true, false. Now, the first two, P and Q, that's the truth table for them remains as it is. The way you create larger truth tables is you take the first, usually the P, and you go for, let's say there's 8 variables. You go true, 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 false, false, false. The next one says Q, you're going to go true, true, false, false, true, true, false, false. Next one says R, it's going to be true, false, true, false, true, false, true, false. So it's just an easier way to organize to see every conceivable outcome. Now, we're going to say here, if, back to this thing, true, true, and true. If P is true and Q is false, it is false because if and only if Q is true. So Q is the thing that's the big determiner. Now, what's going to happen is if, so Q is false, Q is true, now P is false. Now the final one, which is interesting, is if P is false and Q is false, P if and only if Q is true. And that's because, when you think about it, if you say something, like you say to a kid, like, if you clean your room, we're going to go out for ice cream. Well, the kid didn't clean his room and you didn't go out for ice cream. So neither of those conditions were met, but that doesn't in any way challenge the veracity of the original statement. So that, in a sense, remained true or untested, I guess. But anyway, that's how I tend to think of it. Again, this is don't go quoting me to a math professor, you know. Anyway, let's take a look at this here. Okay, so now compare the statement R. Okay, so this is the next page. Hang on a minute here. Is even, all right, let's just go to another page. All right, and all right, 2.4. Compare the statement R such that A is even if and only if A is divisible by 2. So now what we did was, okay, let's go back for a second. Turn this off, turn this on. So if you look at this, this is taking our statements here and combining them and packaging them all up to one more level. Now we're taking all what P and Q, if and only if, and we're just saying that's R now. That conditional, that biconditional, we're assigning it to R. That's what's happening. All right, so now let's continue here. Compare the statement R, yes, with this truth table. If A is even, then the two statements on either side of if and only if are true. So we kind of went over that. If A is odd, the two statements if and only if are false. Okay, it's here. Thus, R's no matter what value A has. So, right. Okay. Now, basically what they were saying is, I already went over this with the true and false statements. They're just explaining that. Now, not surprisingly, there are many ways of saying P if and only if Q in English. So the following constructions all mean P if and only if Q. All right? So, very important. This part's very important. The stuff on page 47 and the stuff on page 44, those English constructions are things that you got to memorize. And you got to memorize them in the exact order where P and the statement and Q lines up. So I'm not going to list them all, but I'm just going to read them. And yeah, this is the kind of thing you got to go and memorize. Since now I'm going to be going into questions, but I'm going to read them first. P, if and only if Q. That's the basic one. P is a necessary and sufficient condition for Q. So P comes first. Is a necessary and sufficient condition for Q. Now, the word for comes before P. This is important. If you see one of these keywords come before P or before Q, such as if comes before P or for, that's the order you're going to have to find it in. So for P, it is necessary and sufficient that Q. And P is equivalent to Q if P, then Q, and conversely. Okay, and... all right, well, let's do some questions now. Without changing their meanings, convert each of the following sentences into a sentence having the form P, if and only if Q. So we don't want to change the meaning of the sentence, but we want to transform it into the P, if and only if Q. That means that the truth value has to be the same as it currently is, but also the meaning has to be, we can't give it a new meaning by rearranging it. We will be rearranging, but the fundamental meaning of what is cause and what's the effect has to remain the same. So, number one. Remember, all the questions are in the back of the book. We're only doing the odds because that way we don't damage the integrity of the book as a teaching tool. All right, so we're going to say for wait a minute. Okay. For matrix A to be invertible, it is necessary. I need to write cleaner. Necessary. Necessary and sufficient that the determinant of A be not equal to 0. So we look, it is necessary and sufficient. So that's one of our examples. For P, it is necessary and sufficient that Q. So after the word that, this is going to be our Q. Before the word, before it is necessary, this is going to be our P. Now, we're going to take these two, then it is necessary and sufficient that gets dropped, and we're going to rewrite P if and only if Q. So we just have to put those words in that order. So it's going to be for matrix. But this is linear algebra. We'll be doing that book. Just want to get a little further ahead in this. There's 6 books that I intend to be doing that I personally need for my own knowledge. 3 of which I've passed, 3 of which I did not. This is one of the ones that I didn't. So again, this is a class I intend to retake. And here we go. For matrix A to be in, this is the reason that I'm doing this, really, is this really makes me Johnny on the spot in terms of having to practice and my chat holding me to account. Okay, so for matrix A to be invertible, that's P. Let's see here, 1 second here. Okay, for matrix to be invertible, that's P, and then we're going to say if and only if for matrix A to be invertible, if and only if, and I'm going to fix that 4 in a second here. That's a problem. 4 is not part of the we're going to rewrite this so the English doesn't sound so weird. Matrix A is invertible if and only if the determinant of A is not equal to 0. Okay, matrix A is invertible if and only if the determinant of A is not equal to 0. Alrighty. Let's go check that. See what the book says. Yeah, so the book wrote basically the same thing. Here it says a matrix is invertible if and only if its determinant is not 0. And I wrote matrix A is invertible if and only if the determinant A is not equal to 0. So essentially they just wrote it more English and less math, but it's the same thing. The P's and the Q's, the if and only if are all lined up. So yeah, that's fine. Next. Okay, 3. If x times y is equal to 0, then x is equal to 0 or y is equal to 0, and conversely. All right, let's see here. If P, comma, then Q, comma, and conversely. So if, let's see here, if P, then Q, and conversely. Okay, now we're going to write it in terms of if, IFF. We're going to say x, let's go a little higher. X times y is equal to 0 if and only if x is equal to 0 or y is equal to 0. Makes sense? All right. Yeah, book agrees. All right. Yeah, that was a very simple one. For an occurrence to become an adventure, it is necessary and sufficient for one to recount it. Jean-Paul Sartre. I don't think I've read. I think maybe I've read just a little bit of Sartre. Anyway, don't have any comment on that. positive or negative. I don't have anything to add. For any occurrence to be an adventure, it is necessary and sufficient for one to recount it. Let's see. So now here's the thing. You look at it, right? I'm going to read the two options we have. We could say P is a necessary and sufficient condition for Q, or for P, it is necessary and sufficient that Q. The for gives it away. If you see a for before the P statement, you have to use that one. Although, to be honest, the P and the Q arrangement remains the same. Either one, the P, the cause, will result in the effect Q. Okay, so let's read it. So write it out first. Okay, so for this is P. It is necessary and sufficient Q. Okay, now we need if and only if P. An occurrence becomes an adventure if and only if one recounts it. So we're going to put it in present tense. Okay. 5. An occurrence becomes an adventure if and only if one recounts it. Perfect. Word for word. All right, next. In other words, yeah, book agrees. What? That's it? Huh. That's it. Okay, yeah, that was short. Okay, well, that's it for 2.4, and I'll just throw the previous one up. Yeah. So there's only 5 questions. We only do odds, so that was only 3. That was this very, very fast section. Okay, so I'm going to wrap this up. I'm going to now do my algebra and trigonometry stream because I didn't do that yesterday. And so this will probably, I'm going to use more time into that. And then maybe I'll stream 2.5. We're going to be making bigger truth tables. And I am really enjoying making truth tables right now. So yeah, that's that could be interesting. Then 2.6, logical equivalences and De Morgan's laws. Okay, 2.6, and then we go to qualifiers in 2.7 and 2.8. This section runs for a while. Yeah, it's gonna be a while. We're about maybe halfway through it, not even. So yeah, we're not even halfway through this. So that's good. This is a nice dense section. I'm really enjoying it. Okay, so I'm gonna end the stream now, and then if you want me to watch me do more math, again, just wait a few minutes. I'll start the algebra and trigonometry stream. All right, see you next time.